Hello students, welcome to Educate. In this video, we will discuss about the isomerism in coordination compound. Previously, we have discussed about how to write the IPAC name of the compound when the formula of the compound will be given, as well as how to write the formula of the compound when IPAC name of the compound has been given. In addition to that, we have already discussed the terminology in the coordination compound as well as the introduction about the coordination compound. So now we will discuss about the isomerism of the coordination compound. So first of all, what is isomerism? Isomerism, what is that? Same as we have studied in the organic chemistry, same here also. So isomerism is the phenomena in which the two compounds have same molecular formula but different properties. Isomerism is the phenomena in which the two compounds have same molecular formula but different properties, and both the compound are called isomers of each other. The phenomena is called isomerism and both compounds are called isomers of each other. Okay, now let's see here. So isomerism is of two types. That means difference in the properties of the compound can be due to two reasons. One is that when there will be difference in the structure, so that will be called a structural isomerism, and when there will be difference in the relative, then when there will be difference in the arrangement of ligands in three-dimensional space, then that will be called stereoisomerism. In stereoisomerism, there will be difference in the arrangement of ligands around the central atom, and in structural isomerism there will be difference in the structure of the coordination compound, and hence there will be difference in the properties of those compounds. Okay, so let's see. Firstly is stereoisomerism. This one is stereoisomerism is of two types. One is called geometrical isomerism and another one is optical isomerism. Geometrical isomerism and optical isomerism. As the name indicate, geometrical isomerism means geometry will be different, and optical isomerism means the optical activity of both the isomers will be different. Both the compound will have same molecular formula, but in case of geometrical isomerism, the geometry of the isomers will be different, and in case of optical isomerism, the optical activity of the compounds will be different. So they will be called geometrical isomers. In case of geometrical isomers, both the compound will have difference in the geometry of the compound, and in optical isomerism the two compounds will have difference in the optical activity. Okay guys, now let's see. Firstly, geometrical isomerism. What is here? How to that? So in the examination, question will be very simple here. So in geometrical cis and trans, you have studied in class 11th about the cis and trans isomers. Very simple here it is. Let's see here, the both the ligand, same type of ligand is on the same side. Here this chlorine and this chlorine is here towards left hand side, and this ammonia and this ammonia both is on towards right hand side. So it will be called cis. And in this molecule here, this chlorine and this chlorine is opposite to each other, and this ammonia and this ammonia, that is opposite to each other. So this one is cis isomers, this one is trans isomers. Okay, can anyone tell which will have greater dipole moment? That's I am giving you in the homework. Think over that. Now that was this was the formula. This type was Ma2B2 type. That means two atoms or ions of the same type and other two of the same type. Now here in Ma4B2 type, here it's also very easy to predict about the cis and trans. So if above and below will be different, then cis, and if same, then trans. Listen, what actually is here, this ammonia is on the same plane. This chlorine and this ammonia is on the same plane. That means here, like cobalt atom here, this one here, this one and this one. Here is ammonia, chlorine and ammonia, and they are on the same plane. This is ammonia and the chlorine on the same plane, and one above and one is below. So if above and below, you will have to consider in case of Ma4B2 type, the compound will be cis or trans. In that case, you will have to check the ions or molecules above and below are same or are different. If same, then trans, and if different, then cis. You will have to consider that the compound present above and below, that is same or different. If that will be same, then trans, and if different, then cis. Like in this molecule, that means this ammonia, this chlorine, this ammonia, these are on the same plane. That is here, cobalt here, here. They are on the four corners of a square, and one chlorine above and one ammonia below. So above and below are different. So that's why cis. And here above and below is different, then trans. In Ma4B2 type, you will have to consider only the ligand which is present above and below. If above and below is same, then trans. Like this ammonia, these ammonia are on the same plane. Like here ammonia, like here cobalt, then here ammonia, and here ammonia. So these are same, and here chlorine above and chlorine below. That is same. So same type of ligand is on the opposite direction. So that's why it is trans, and here the above and below ligands are different. That's why it is cis. Here this one above and below. Above and below is different. So that's why cis. Here above and below is same. That's why trans. Where is it is? Listen, in this case, when the bidentate ligand, if bidentate ligand here, ethane 1,2-diamine is a bidentate ligand. During that course, in case of A2C2 type, A2 means this one is unidentate ligand, and C is didentate ligand. Unidentate ligand and bidentate ligand. You will have to consider about the bidentate ligand. If bidentate ligand will be on the same plane, then that will be trans. If the bidentate ligand will be on the same plane, then that will be trans. And if the bidentate ligand will be, the two bidentate ligand will be on the two different plane, then that will be cis. Let's see here. I am drawing the phase diagram for this one. Suppose this compound. So actually what's the structure here? Here is cobalt, four corners of the same plane, like cobalt here. So one here, one here, one here, and one here. That means four corners of a plane. That's we are mentioning here. And one is above and one is below. Here it is ethane 1,2 diamine is on this plane. That means on this plane here. And this one here, ethane 1,2 diamine is on this plane. Here chlorine, here chlorine. So now let's say structure. This one, here this plane, here this plane. So that means the bidentate ligand is on two different planes. Here the bidentate ligand is on two different planes. That's why it is cis. That's why it is cis. But here, in this case, cobalt here, this one is four corners of the same plane, one above, one below. Here is ethane 1,2 diamine, this one, and here ethane 1,2 diamine. So this one is same plane, and this chlorine, same plane. So that means bidentate ligand is on the same plane. That's why it is trans. Okay. In the same way, another compound can be also drawn. As for example, let's see. Suppose this compound here, cobalt. So in this case also, what is here? This bidentate ligand is on this plane, just like this plane. And this bidentate ligand is on this plane, any of the corner like this or like this. So here that is on the two different planes. That's why it is cis. And if like that, like this one. So here the ethane 1,2 diamine is on this plane, above plane, and this one is also on this plane. That means ethane 1,2 diamine, one is on here, another one is here from below. So that is on the same plane. Bidentate ligand is on same plane. So that's why it will be trans. It will be cis because bidentate ligand is on same plane. So it is cis. Guys, very easy it is. Here you will have to just only watch out that the two bidentate ligand present is on the same plane or is on different plane. If the bidentate ligand will be on the same plane, then that will be called trans, and if the bidentate ligand will be on different plane, then that will be called cis. Okay, now let's see here. Facial and meridional. About facial and meridional isomers. Listen here. This NO2 and below NO2. That is bonding here. So like here, cobalt here. So here NO2, here NO2 and here NO2. So that will form here. So that will be called facial. But here, this NO2 and this NO2. There cannot be form a fish. So that will be called meridional. Means these NO2 are on, that means two corner here and this corner. So triangle could be formed, but that means two triangle here and cannot be joined here. So that is facial and meridional. Let's see here. Here, why is geometrical isomerism not possible in tetrahedral complexes having two different types of united ligands coordinated with this one? What is there here? In case of tetrahedral complex, what's the arrangement? The arrangement of the ligands will be like that. That is not only valid only for the coordination compound, but for the organic compound also. So when you consider tetrahedral geometry is this one. So relative arrangement of this group will be same, because everywhere here bond angle 109.5 degree, here also 109.5 degree, this one 109.5 degree, this one 109.5 degree, this one also 109.5 degree, this one also 109.5 degree. That means the relative arrangement of ligands in three-dimensional space will be same. By inside you rotate. So relative arrangement of ligands around the central atom is same. So that's why the tetrahedral complex do not show stereoisomerism. Okay, or that not shows geometrical isomerism. Okay, any problem, guys? So that was about facial and meridional, and that was here why the tetrahedral complex do not shows geometrical isomerism, like Ma2B2 type. In case of compounds having Ma2B2 type, so Ma2B2, so shape may be tetrahedral as well as square planar. Tetrahedral, the shape of this compound Ma2B2 type will have the shape of tetrahedral as well as a square planar, of which the compound whose shape will be a square planar, that can only show the geometrical isomerism. That is, cis and trans isomers will form in only those coordination compound having the formula Ma2B2 type, whose shape will be a square planar, and the coordination compound whose shape will be tetrahedral, that will not show geometrical isomerism. Because in the tetrahedral complex, the relative arrangement of ligands in three-dimensional space will be same. Clear? Now let's see optical isomerism. First of all, what is optical isomerism? So in the short, I have told you what is optical isomerism. That means the compounds which will have same molecular formula, but they rotate the plane polarized light in opposite direction. They will be called optical isomers of each other. Okay, what is plane polarized light? In the chapter of halocene and halodene also you will study, but listen here also. First of all, what is transverse wave and the longitudinal wave? Transverse wave is what and longitudinal wave is what? Let's see. When suppose here there is a string here, this is a string here. Now when you will jerk this string, then what happen? This type of shape you observe. So this type of shape you will observe. What actually is? It is this one. Here this particle will go above, go to the maximum, and then after again will come down, go to the maximum, and again go to this one. That means this constituent particles is not going this side. When you jerk here, then this particle will oscillate above and below. Same here, these particles will oscillate above and below. This particle will oscillate above and below. This particle will oscillate above and below. But the wave will comes from this point to this point. In this manner, wave will approach toward this side. So direction of wave is this one. It is direction of wave. And the constituent particle is oscillating in this direction. So direction of so this direction, this is so constituent particles will suppose vibrate above and below, and the wave will vibrate in this one. So that means here the constituent particles vibrate perpendicular to the propagation of wave. This type of wave is called transverse wave. Transverse wave is the wave in which the constituent particles vibrates in the direction or vibrates perpendicular to the direction of propagation of wave. Transverse wave is the wave in which the constituent particles vibrates perpendicular to the direction of propagation of waves. As for example, when you jerk the string, same as when you have seen in the sea, the beaches of sea or of the river. Suppose here you are at the bank here, so river here, so constituent particles vibrates above and below. Then after again starts from this particle, from this portion the constituent particles oscillates. Then after from this particle, then after it will come here, this particle will oscillate. Then after this particle will oscillate, then after this particle will oscillate. So what happened? Wave will move in this direction. Wave will move in this direction, and in this direction constituent particles will vibrate. So here constituent particles vibrates in this direction, wave comes in this direction. So here the direction of oscillation of particles is perpendicular to the direction of propagation of wave. So this type of wave is called transverse wave. Okay, not only this one of them, the best example is the light. So light is a type of transverse wave. Keep in the mind. So very frankly, I am telling you about that light wave, that this one is important for your CUET examination, but neither for your IIT main or the NEET examination or the 12th board examination. Frankly speaking, this question will not ask in your 12th board examination or IIT or in NEET examination, but this can ask in the CUET examination. That light is a type of transverse wave, B longitudinal wave. No, that was transverse wave. So you may write that transverse wave is the wave in which the constituent particles oscillates perpendicular to the direction of propagation of wave. Now longitudinal wave, let's see. Consider about in a spring. In case of a spring like this. Here drawing on the whiteboard is difficult. So what happened in the spring when you will compress them, this side. So here that will be denser and this portion here will be rarer. Then after this particle will tends to come this side. So again this portion will become denser and this again rarer. Here also rarer medium already. then after this particle will tends to move in this direction. So constituent particles is moving in this direction, and wave is also moving in this direction. So it is direction of this is the direction of oscillation of constituent particles, and it is the direction of wave. So in this direction, that means this is called a longitudinal wave. That means the waves in which the constituent particles oscillates in the direction of propagation of wave, that type of wave will be called longitudinal wave. Okay, the wave in which the constituent particles oscillates in the direction of wave, that is called longitudinal wave. Okay, and its best example is that was here in the spring, same thing happened, and that is for the sound wave also. What happened in the sound waves? The air particles nearer to the source of the sound, near to the vibration, that gets dense, then after that will propagate in that direction. So same here, example is sound wave. So light wave is an example of transverse wave, while the sound wave is an example of longitudinal wave. Light wave is a type of transverse wave, and sound wave is a type of longitudinal wave. Okay, so that was about this one. What is transverse wave and longitudinal wave? I have considered that you might don't know about those points, so that's why I have taught. Maybe a number of students have the information about the longitudinal wave and the transverse wave, depending on if you have studied in the physics carefully or not. Let's see now here. Before that, you think along a line, how much perpendicular can be drawn? That means suppose this is a line, how much there will be a plane which will be perpendicular to this line. And before that, one also you consider from a point how much line can be drawn. You can draw how much lines from a point. Think? I am waiting. You think? Now let's see about the first question. Suppose this is a line. So this is a perpendicular. This plane is perpendicular. This plane is also 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 perpendicular. So along there will be infinite planes which will be perpendicular to a line. That means there will be infinite plane perpendicular to a line. So that is here, and second one here, second question was from a point how much line you can draw. So you can draw that means from a point infinite lines can be drawn. Okay, so same here. What happened in case of ordinary light? That means the light emitted from sun, star also, or your tube light like this one. So that is ordinary source of light. So your candle also. So light emit, in case of ordinary light, the constituent particles vibrates in all the plane which are perpendicular to the direction of propagation of wave. Like this plane here, constituent particles will vibrate in this plane also. Like this plane here, constituent particles will vibrate in this plane also. Same here, this one. So in case of ordinary light, the constituent particles oscillates in all the planes perpendicular to the direction of propagation of light. When that ordinary light will pass through Nichols prism, when the ordinary light will pass through Nichols prism, then the constituent particles will start moving. Then the constituent particles will start moving in a single plane. When the ordinary light will pass through Nichols prism, then the constituent particles will vibrate in a single plane which will be perpendicular to the direction of propagation of wave, and that light will be called plane polarized light. That light will be called plane okay. Now the compound, there is a compound, and if the plane polarized light passes and the constituent particles will bend towards right, when the plane polarized light pass through the solution or through the compounds, through vapor, then the constituent particles, then the plane polarized light will bend towards right. Then the compound will be called dextro-rotatory compound. Dextro-rotatory. And when after passing through the solution, the plane polarized light will bend towards left, then the compound will be called levorotatory compound. When the plane polarized light after passing through the compound will bend towards left, then that compound will be called levorotatory compound. Okay, dextrorotatory compound and levorotatory compound. That was the meaning of that. Now, and that is here, a compound will be optically active if that will form here non-superimposable mirror image. Okay, that will form non-superimposable mirror image. Then only that compound will be optically active. So let's see here. So how to predict that the compound is levorotatory or dextrorotatory? In the examination, that only you will have to answer. In the co-examination, in the IIT main examination or in the NEET examination, the shape of the molecule will be provided and will ask this compound is levorotatory or dextrorotatory, or is a racemic mixture, or is optically inactive. So in case of coordination compound, only you will have to consider about the bidentate ligand. If the bidentate ligand will be towards right, then compound will be levorotatory. In which direction will be the bidentate ligand? Optical activity will be opposite to that. If the bidentate ligand will be towards, or here particularly ethane 1,2-diamine. If ethane 1,2-diamine will be towards right, then the compound will be levorotatory compound. And if the ethane 1,2-diamine will be towards left, then compound will be dextrorotatory. if ethane 1,2-diamine will be towards right, then the compound will be levorotatory, and if the ethane 1,2-diamine will be towards left, then the compound will be dextrorotatory. Okay, so let's check in this compound. Here ethane 1,2-diamine is towards left, so compound will be dextrorotatory. Here ethane 1,2-diamine is towards right, so that's why levorotatory. Same here in this compound, ethane 1,2-diamine is towards left, so dextrorotatory. Ethane 1,2-diamine is towards right, so levorotatory. So any problem here? Only that you will have to watch, that ethane 1,2-diamine is whatever be the structure, you will not have to consider anything about that. Apart from that, ethane 1,2-diamine is towards right hand side or towards left hand side, you will not have to consider anything else. So simple here it is. So now here also, okay, we have discussed already. Okay, now let's see, watch out this question. You know already that only covalent bond is directional. So the shape of the molecule will be also always considered by the covalent compound. Like that, what's the shape of PCl5 you have studied, but what is the shape of KCl? No any questions we have might be seen. Okay, so shape, because covalent bond is the directional and ionic bond is non-directional. We always keep in your mind, that will be important. This information will be important for your NEET examination and the IIT examination, and more important is for NEET examination. Okay, let's see. Lots of watch out here. Draw structure of numerical isomers of this one. Okay, here it is. This compound is Ma2B2 type. Ma2. Okay, B4 type. Ma2B4 type. So obviously, if A2 will be opposite to each other, like M here, BB on this one, BB on this one, and here AA, so that will be trans. If at any place you keep B here and A here, or from here or here, or here, from any corner, if there be exchange of ligand with the perpendicular plane, then that will be cis, otherwise trans. So in this compound here, watch out, this compound and this compound here is opposite. This ligand and this ligand is both is opposite, so that is cis. Now here this ammonia and this ammonia is opposite, so that's why trans. If there is CN and CN here also, like if here, if that is, see, if anywhere opposite, then that will be trans. Okay. Now in this compound, here cis and trans is that. Now let's see here. Which is chiral and optically active, oxalate ion, and this one here. So let's see here. Draw the structure. Cis and trans. So draw here about the cis and trans. So in cis, optical activity will be here, cis above and below here, this compound. So oxalate ion is neither left nor right. Okay. And here, this one and this one, in both the cases, both will cancel out to each other. Both the bidentate ligand will cancel out each other dipole moment. That's why this one is optically inactive. This compound trans will be optically inactive. Okay. It's all for the, that was about the geometrical stereoisomerism. Once again, recall what happened in geometrical isomerism. There will be difference in the properties due to difference in the arrangement of ligands around the central atom. Okay, that will be a stereoisomerism. Now let's see a structural isomerism. In a structural isomerism, there will be difference in the properties of the compound due to difference in the structure of the compound. Okay, so there will be difference in the properties of compound due to difference in the structure of the compound. And there is actually here 4 types of structural isomerism. Listen, first one here is linkage isomerism. So in case of linkage isomerism, here linkage isomerism, this linkage isomerism will be shown by those coordination compound which will contain ambidentate ligand. The linkage isomerism will be shown by those coordination compound which will contain ambidentate ligand. As the name indicates, linkage isomerism. That means there will be difference in the linking. As for example, this compound, when you will have to write the IPAC name of this compound, so that will be here, IPAC name of this compound will be pentaamine nitrito-N. NO2 here is the ambidentate ligand, and here written NO2, so that's why we write nitrito-N. Okay, now same here, if that there will be on the place of that one, if there be ONO, that means that will be written like this. That one. So IPAC name will be different. Here the nitrito group is bonded to the cobalt through nitrogen. But in case of ONO, this ligand is bonded to the cobalt through oxygen. So on the place when we write the IPAC name of the compound, so either we will write isonitrito. Here on the place of nitrito-N, we will write isonitrito. Okay, or nitrito O. So IPAC name will be here different, and linkage isomerism there will be. That means linkage isomerism will be shown by those coordination compound which will contain ambidentate ligand. In the examination, either in 12th board examination, it will not ask that what define the linkage isomerism. But in case of 12th board examination as well as in NEET and less chances in IIT main examination, but its probability of asking the question cannot be said that it's nil, and there is high probability of asking the question in CUET also, that compound will be given and will ask among these compounds which could show linkage isomerism. So during that course, you will have to, in that option, you will have to watch out among those coordination compound which compound contain the ambidentate ligand. That means the coordination compound which will contain the ambidentate ligand, that will show linkage isomerism. Okay. Now let's see here coordination isomerism. What happened in coordination isomerism? The coordination isomerism will be shown by those coordination compound in which the cation will be coordination sphere as well as the anion will be also coordination sphere. So coordination isomerism will be shown by those coordination compound in which the cation will be coordination sphere as well as the anion will be coordination sphere. So let's see how to write the IPAC name of this compound, like this compound. So how to write the IPAC name? So this compound and this compound, watch out. Same here, but here ligand here, cobalt has came here, chromium. This one the ligand. Cobalt came this side, chromium that side. So what's the IPAC name of this compound here? This compound, the IPAC name will be listen here, in this case, here the oxidation number will be equally divided. So chromium is this one. So what will be the oxidation number of this cobalt? Same as the chromium. So here -6, that's so here +3 and here also +3. So oxidation number of cobalt will be +3 and that of chromium, that will be also 3. That is, and what's the IPAC name of this compound? So let's see its oxidation number. So same here also 3 and here also 3. So here that is isomerism is due to difference in by the exchange of central atom. Here isomerism has been formed by the exchange of central atom. Here chromium, here cobalt. Now chromium came here, cobalt gone there. So coordination isomerism will be shown by those coordination compounds in which the cation as well as anion both will be the coordination sphere. Let's see then after is ionization isomerism. As the name indicate, ionization means when it will be dissolved in water, when the compound will dissolve in water, they will provide different types of ions. That will be called ionization isomerism. Ionization isomerism means the phenomena in which the two compounds will have same molecular formula, but when dissolved in water will give different types of ions. That will be called ionization isomerism. Let's see about this one by the formula example. I shall not go to write the IPAC name here. Simply just consider here ionization like this compound. Very easily you can write the IPAC name. That's why I am not writing the IPAC name. Yeah, it is a fact that when the IPAC name will be same, that means compound is same. And if IPAC name will be different, then the two compound is different. But here let's see. So here in bromide ion is outside the sphere. So when the sulfate ion it is inside the square bracket, that means the sulfate ion is covalently bonded to the cobalt, but the bromide ion is ionically bonded with the cobalt, and only the ionic bond get dissociates. So when that will dissolve in water, then what's the ion you will get? So inside the sphere that will not get dissociate. So that will be so this compound will get the test for bromide ion and not for the sulfate ion. And to this compound, when it will dissolve, here sulfate is outside the square bracket. Sulfate ion is outside the square bracket and bromide ion is inside the square bracket. So that means the bromide ion is bonded to the cobalt through covalent bond, while the sulfate ion is bonded to the cobalt through ionic bond. Only ionic bond dissociates. So on dissociation in water, when this compound will dissolve in water, then what's the ion it will give? So this compound will give the test for sulfate, but not for the bromide. And this compound will give the test for the bromide ion, but not for the sulfate ion. So both the compound are called ionization isomerism. Keep in the mind, there is bigger difference, and some students get confused in the ionization isomerism and in case of solvate isomerism. In ionization isomerism, on dissolution in water, the compound gives different types of ions, while in case of solvate isomerism, the compounds on dissolution in water give different number of ions. In ionization isomerism, on dissolution in water, the compounds give different types of ions, while in solvate isomerism, the compounds give different number of ions. What's the solvate isomerism? That will be, just watch. Here, let's see about this compound. Let this compound here. So here outside the bracket is chlorine, 3 chloride ion. And here outside the bracket is 2 chloride ion. So when it will dissolve in water, that will give 3 moles of chloride ion. But this compound, when dissolved in water, will give 2 moles of chloride ion. So this compound gives 3 moles of chloride ion, and this compound gives 2 moles of chloride ion. So this is solvate isomerism. That is also called hydrate isomerism. So this is called solvate isomerism. In solvate isomerism, the 2 isomers gives different number of ions when dissolved in water. Okay, that was solvate isomerism. Let's see about this compound here. About this compound, let's see that compound, which type of isomerism it will show. So that can show optical isomerism also, that means dextrorotatory or lever rotatory. That compound can show geometrical isomerism also. Okay, but among the structural isomerism, that cannot show ionization isomerism or linkage isomerism or solvate isomerism or the coordination isomerism. So this one can show only stereoisomerism and stereoisomerism, that means geometrical as well as optical also. Here ethane 1,2-diamine, here 3 is there. So that can be here same, it can show geometrical isomerism as well as optical isomerism. So this can also show stereoisomerism. This compound can show the linkage isomerism, where NO2 ambidextrous ligand here is. That's why that can show the linkage isomerism. That can show ionization isomerism also, if NO2 will come there, this side. But that will not show solvate isomerism. Now about this compound. Here, this compound can show 1, 2 to 4. So that can also show cis-trans isomerism, this one. Now, given this one and this one are ionization isomerism. Okay, so this compound on dissolution will give the test for sulfate ion, and this compound when dissolved in water will give the test for chloride ion. So this compound and this compound is type of ionization isomers. That means this compound and this compound are ionization isomers of each other. Clear? So here in the next class we will discuss about bonding in coordination compounds. Here, valence bond theory, and this topic is also highly important because questions asks that which among these compounds which is paramagnetic and which is diamagnetic, which we explained by the valence bond theory. This valence bond theory will be helpful for to predict the shape of the molecules, that means coordination polyhedron, as well as the magnetic properties, that means the compound will be diamagnetic or the paramagnetic. So this valence bond theory, about that we will discuss in the next class. It's all for the today class. Thank you, Team Educate.